Thank you very much. Really, at first, only for the first slide, I would like to share for you the history of this Oncothermia, how it was somehow deviating from hypothermia. I was established a company in '88, and then a long period was then it was marketed. In 2002, we established a German company, and then from that one, we published really a lot. This book was the main point which we published together with my family members, my son and daughter. And then in Japan, we published also, and some books are definite chapters about Oncothermia. A lot of other publications, about 300, more than 300 publications from that time. More than 30 are patent registered. Many of those are not because more technical. More than 40 patents published, and then here's a certificate about the Nanothermia, which today I would like to speak. So my outline is very simple. Trend of hypothermia, nanoheating, temperature distribution, temperature back, and temperature in Oncothermia, Nanothermia. So, as first I would like to remind you what is the problem with the hypothermia in general. If there is a tumor and we are heating up locally, then we increase the local temperature if we are doing the focus. So we have a self-destruction potential by heating. But of course the heat will spread over and increasing the blood flow, the blood perfusion. Of course, in the tumor it could be decreased because of the structure of the tumor vessels. But outside, in the healthy tissue, is increased. The increased blood flow here could energize the tumor, so the tumor living part, which is the outside part of the tumor, like a balloon, it goes. So energizing potential by the glucose delivery, and metastatic potential by the blood flow, which is intensive around. So it means that if it's too high difference between the tumor inside and on the microenvironment of this one, it could be a competition between the effects. So this feedback, which increases the blood flow on such way and somehow makes a contra-effects or killing mechanism, has to be somehow controlled, and this is which Oncothermia would like to do with the nanoheating technology. First, what is the difference between the conventional and nanoheating? Conventional heating is always going from the surface to inside, and some convection currents are heating up the full volume. In the nanoheating, you are heating up inside of the target, the different points, and regardless of that one, what is the surface or how the surface reacts. So in the nanoheating example, for example, if the gold nanoparticles in the eyes, then very soon it will be water around in the eyes, and which is very interesting that if the particle is 20 nanometers in size, then about 40 nanometers, so two times more larger area, it will go down the temperature. So it means that it's not a good heater everywhere, only in a very limited part. Very interesting that it's an FDA approval sterilization, which is really a nano heating, or it looks like nano heating. It's a microwave heating, microwave sterilization. You can see that the sterilization efficacy is much better with microwave, with 2.5 minutes to what was 2 per centimeter, while the conventional has 40 minutes, 120 centigrade, and the lethal effect is much better in microwave, about 1 order of magnitude or more than 1 order of magnitude quicker. This could be shown in different other, it's all FDA approved, FDA draft website I have taken these. So you can see that the bacteria can be killed very easily, microscopically, without that one not heating up everything, only the bacteria is necessary. The absorbed energy is calculated, which is the same like with us, and the frequencies which they are using is also in the FDA side, then the 13.56 megahertz is involved. Okay, then what is the temperature distribution when we are doing nanoheating? So here is, let's say, an example of the tissue. Then we would like to heat up only a nanoscopic points, which you have to select somehow. Later I will tell you that how to select it. Of course, 36 centigrade is the full area, and then we start to heat up only the nanopoints. Maybe the nanopoint can be 50, but the full average could be only 38, because the nanopoints are very quickly cooled down by the environment. So when you are going 40, then of course the points are larger and larger, and then even if it remains 50, very soon you can have 44 in all, but obviously you have lost the selectivity totally. No selection at all later on this one, and then those feedback effects which we would like to avoid could be a problem. So if you have even higher, then of course you can heat up very much on the large area. So this is also a 1 millimeter step-by-step picture how to heat up, and you see that later you can heat up everything, but maybe that the most optimal is somewhere here. So if we have a nanoparticle, then as I told, we have let's say photodynamic therapy or some other heating methods, we heat it up and then very soon goes down. You see that the temperature change, and it could be shown that the nanoparticle is 70 centigrade higher than the environment, but very soon in nanometer range it goes down to the zero, so the norm temperature thing, which means that one that could be very, very heated without that one, that heating up everything. This could be seen in the near temperature limiting. So the limit of the heating up of the nanoparticle is 43, but depending on the percentage of the nanoparticle, the full area, full target which is heated up is much less. It's only 38 or maximum 30. So Oncologic treatment is such one that we have starting to treat the tumor, and then the real hyperthermia effect, which I would like to show, that is in the rafts of the cell membrane. We are choosing the rafts which have totally different behavior. So the rafts are the clusters of the transmembrane proteins. These transmembrane proteins will catch the heat. So this is the hyperthermia step. And then this will heat up the cells, which you can select with a special selection of the autonomy, which supports the alpha beta states, and then we can select the tumor by the conductivity, by the effect of glycolysis. So it means that this is the hyperthermia step, and this hyperthermia step will heat up this full range of this one, and the full range is over with the re-establishing of the dynamic complexity with time factor modulation and stochastic resonance. This one, the stochastic resonance, is different in different range of size. So here the pattern recognition is important. Here the promote of polymerize the protein connections like E-covering and so on, which was measured many times. And here promote the enzymatic processes, which are so-called ratchet mechanisms, which was discovered at MIT by Estonian and Viva investigators. What about the temperature? The temperature here could be 45 or more. Here the temperature is only 41. Here the temperature is a little bit more than 38. And of course, in the full body temperature is about 37. So it means that the temperature is not equal everywhere. But in the membrane cells, it could be very high. And what is the important point? It acts on the membrane and kills the tumor cells by this membrane action. Temperature effect in cellular level, it's very, very easy to understand that how to measure, because the cell has very special temperature sensor. This temperature sensor is called TRP sensors. It's a temperature and the pain and the two pain limits. And these are the sensors which are really it's a transition receptor potential volumeric receptor, different receptors, and of course all receptors which we would like to measure, that is the TRPV1, because the TRPV1 is sensitive over 42 centigrade. but some of the receptors are sensitive for lower centigrade. So this is the temperature, and then the different receptors are showing very well that what is the temperature on the cell. This is the cellular receptor, which is of course involved in the nerve pain sensing as well. It's not an old knowledge, because in last year it was really fully discovered this thing. So it's of course much earlier discovered, but the full investigation was finished in last year. You can see from the literature that it's co-existent and co-expressed with the HSP70. So it means that the TRPV1 and HSP70 membrane localization is very important, and you can see also in HSP90 and HSP27 and beta-actin together, these are coexisting with the TRPV1. There is a different experiments. I show only one, but how to measure the nanoparticles, nanoparticle or nano heating with TRPV1. This is a nanoparticle with zero magnetic field. This is a magnetic field with something. The nanoparticles are heated up. That heats up the membrane, and the membrane heating will open the TRPV1. So it means that the calcium will go into the cell very dramatically. This is the calibration curve, which is compared to a calibrator. And here is on the reference curve, you can see that the temperature can be measured by this calibration, that the temperature is higher and higher, the temperature on the membrane, so it's really the membrane temperature, which they are measuring with the nanoparticles. So how the Oncotherm then can go to this membrane things. Here are two models of the membrane, but we are using this more modern something when the rafts could be caged because they interpreted in the clusters. And this membrane catching is such one that here you have a raft, this raft, and then raft can be moved. So this raft can be moved on the membrane by the electric field. And this is in the raft is 10 nanometer range, and this electric field will move it in the membrane. So this is the membrane structure of the raft. It's many publications about it. It's new knowledge, and we have in silico models, which one student had calculated with the top facility in the Catholic University, top calculation facility. This is the best in Hungary, and then she could show that what is the specific absorption rate on the raft, and you can see that it's about 6 orders of magnitude higher the raft absorption in lateral dimension, and then in transverse direction also. So it means that somehow in silico it could be shown. This is the heat flow, which in silico is shown. The rafts are here, and the membrane and the extra and intercellular is a current density and heat density, and this is a dielectric loss, which dielectric loss really shows that inside of the cell is very active the things, and then it is an enlargement of this one and enlargement of that. Okay, then let me go to the most important thing, the temperature in Oncothermia, so nanothermia, how we measure, how we use these things for that one that really to prove the nanoscopic range heating. Of course, the research is in progress, so it's not finished yet, but some things I can show, and very soon, probably at the end of the year, we will finish the full study. This study, it shows us first the reference. So then we have two heating, hyperthermia heating and oncothermia heating. Both are in a flask which is heated by a heating plate or by oncothermia method. Then you can have a luciferase GFP transfected into the DNA, and then you can see that the heating pattern is absolutely the same, so each proteins and everything is the same. And which is interesting, that hyperthermia and oncothermia has the same temperature inside the cell and outside the cell. So it means the reference is that one that is verified, that if we measure the temperature outside, that is the inside temperature as well. So all the effects which could be happened, and I will show, that could be only between. So it means on the membrane, which I will show, of course, of the membrane effect. But this is very important that really the outside and inside temperature, because the luciferase is the inside measuring, the outside we measured by the pattern. So it means these are equivalent. At first we used the well-known lab-on-a-chip method. You know it very well, so I will not go in. So this is Oncothermia lab-on-a-chip, and this is Hyperthermia lab-on-a-chip. Oh, you can see that Hyperthermia has much more gene up and down regulation than Oncothermia has. This is the up and down regulation, Oncothermia and Hyperthermia, Oncothermia and Hyperthermia. This is the temperature which is there. So it could be that then the Oncothermia is not so good. But if we study the cross effect between Oncothermia and Hyperthermia, then you can see that totally different genes are up and down in the different things. So it means they are not equal, despite of that one that the temperatures are equal. The temperature is 42.3, 42 42.1. So it means that the Hyperthermia up and down regulation is overlapping, but not identical with the Oncothermia up and down regulation. Then we can go to the microscopic things, also comparing the Oncothermia treatment with Hyperthermia treatment. Hyperthermia it was done in Japan presently, in Toyama University, and you can see that it's very well kept in the water bath and here the Oncothermia. The temperature growth is the same, so very careful things. Even to do that one, that Oncothermia is less than Hyperthermia. This is the staining, which you can see that 42 centigrade does totally different effects. Oncothermia has a lot of apoptotic bodies, so the apoptosis is on, which we have shown in many publications before. This is the treatment comparison with the various temperatures. You see that the apoptosis and live and late apoptosis immediately after the treatment, so it's zero or post-treatment is such one. 3 hours after the treatment, the apoptosis is much more in the Oncothermia. The temperature here is less than the temperature was here, so even it was more in the average temperature, really. And then the total cell count after 24 hours post-treatment, you can see 44 and 42 centigrade, so the Hyperthermia was higher. Oncothermia had much more killing rate in a lower overall temperature than Hyperthermia did. This was proven with slope thickness cytometry, so it means that it's really absolutely proven point. 42, 43, 44 and 42 above almost equal, but even 42 is better for Oncothermia. Then let me study the Hyperthermia effect, so the temperature effect. We know it very well from the literature that the Arrhenius plot characterizes the real temperature effect. The Arrhenius figure is there, and we know it very well from the literature that this is for proteins and cells and so on, has the A and E has a good correlation. This one, which we had measured in this cell line in Toyama, that Hyperthermia and Oncothermia both are satisfying the activation energy, so it means both are thermal processes. Both are thermal processes of different activation energies and different rates, of course. This means that if you calculate the normal CM, so the official dose per meter, then this official dose per meter in Oncothermia also can be introduced, only the R would be different than the R in the Oncothermia, in the Hyperthermia. The R in this case much larger than Oncothermia has. So this is the two logarithmic scales. Then we go from the Roberts over the Arrhenius, we go to the normal temperature sinks. This is hyperthermia, this is oncothermia. And then we use a calibration curve because of the calibration which I had shown before. We use the calibration curve for temperature, the hyperthermia. Then the calibration will be that one, but if it's 42, then by 42 you have 5, but you measure oncothermia 25, so this 25 corresponds is 45. So it means that this difference is really on the membrane. So it means that the difference between oncothermia and hyperthermia is very large, despite of that one, that the measured temperature, the overall temperature, would be the same. So even if you can go in lower temperatures, at least 3 centigrade difference is on. This growth which we have here, it very well corresponds with the earlier measurements which was done in vivo and was published in 2009. So it means that all the system is correlating together with the earlier results. Here is the oncothermia temperature calibration. You see that this is the oncothermia temperature which you can measure, and this is the corresponding temperature which is coming from the calibration curve. So if you measure this oncothermia, let's say 38 point something, then that is 40, or 39, that is 41, and so on, which the difference is caused by the membrane effects. Really, it's a membrane. Then I can show for you that yes, it is. This is another microscope measurement, the calcium influx measurement from different things. This is an electromagnetic fitting. Technically, it's a very, very complicated measurement because it is a very expensive microscope and it's not so easy to apply something on it. Then we did the following: the temperature pattern, which we used. This is the average of the temperature, which is there, and this is the bar which was on and off here, and the line was HD 29. This is the calcium influx, which we have measured. Of course, it's very noisy, but you can see very well with the Weinberg fraction, with the physiological function, the fitting, and it well follows the temperature growth. And then you switch off, it remains because the calcium influx is not so quick. The calcium extracts is not so quick. Influx is. This is the hyperthermia influx, also measured on the same day. And this is the Weinberg function and sorry. And these points which are here, unfortunately, really the handling problem, because we could not heat up equally everything. So it means that this is the surface of the heating, which was overheated. And if overheated, then of course you have a lot of points which are out. This is the oncothermia which we have, and then this is together. So it means that oncothermia opens earlier than hyperthermia opens, and then oncothermia opens again. This one is the other TRPV calcium channels probably, and this is the probably TRPV1 channel. And of course we have to measure here more, but the error, hypothermia, but the error here was so large that we could not really measure. That is why I thought that really it's in progress. But you can see very well that the 3-4 centigrade between the opening of the channels is here also valid. So it means that we are exactly on the membrane, because this is a membrane opening. We are measuring on the same way like the nanoparticles are measuring. So we are really exactly on the membrane with that difference which I have shown before. So research is in progress. So temperature is oncothermia and nanothermia. Take-home message I would like to give very quickly. I use a quoting from Albert Einstein, who is really the star of the science and probably much more a message than my message. So once we can accept all limits, we go beyond them. It's very important. We have to realize our limits in hypothermia. Have we recognized our limits yet? I think we started. The other one, we can solve the problem by using the same, we cannot solve the problem by using the same kind of thinking we used when we created that. That is the question. Do we think differently? I think just we started. So I think many times I'm telling, and I would like again to tell, take the complexity into consideration. Never keep the tumor alone. Treat the patient always in its complexity, and then you will be successful. I don't think so that all force is all muscles to heat up everything with a complex distortion strategy, with SAM dose and so on. All strategy has to be different. The survival time and quality of life is our aim, not only that one that is destroy the tumor. And for this one you need selectivity and a good treatment strategy. So this is my message. Thank you.